Here's some practice with solving quadratic equations. The first one, we're going to solve that equation. Now, it doesn't say solve for a particular variable, but since there is only one variable, there should be no confusion. We are solving this for the variable t. There are multiple ways to start this off. One thing we might do is multiply out this binomial, recollect all our terms, and see if we get something that can factor, or multiply it out, collect all our terms, apply the quadratic formula, or not. Or let's just apply algebraic principles to whittle our way in towards the t. If we're going to try to dig our way in towards the t from the outside, the first thing that has to go away is the plus 10. And so what I will do is subtract 10 from both sides, and I will be left with t plus 5 squared equals 7. And now, as I'm digging my way into the 5, the next thing that has to go is the 2, the exponent of 2. So I'm going to take the square root of both sides, which will leave me with t plus 5 equals the square root of 7. Now, over here, I'll just make a note that sometimes you could interpret that as, you have that plus minus ambiguity that you hear of sometimes, where we took a square root and it could have been plus or minus square root of 7 instead of just square root of 7. Philosophically, there's a couple of different ways you can approach that. We could start carrying around that whole plus minus, or we can take the alternate attack on the problem, which is just to assume that we are using the square root function whose domain and range are adapted so that there is only one output from the function, and that would be the positive output. Then we subtract 5. And so that is our answer. Now, unless you have a reason to, do not start going button pushy on your calculator. This is the best way to write that number. It is in its most exact form. If you go grab your calculator, punch in a 7, punch the square root button, and start writing down a decimal approximation, you're going to be changing from an exact number to an estimate, and you're actually doing more work than you need to. So just leave it alone. All right. This particular equation, again, just like the one above, there's multiple different ways to start off. I could subtract the 13 over to this side and see if I get something that could factor, or I could subtract the 13 over here and use the quadratic formula. But what I'm going to do instead is start with this particular process, or this object, and see if I can't give it a form something like the one up here. Okay, so again, one of my options, I'm going to take option 1. You haven't seen what it is. The other option, or options, would be to bring that 13 over there. You can't factor it. You'd have to use the quadratic formula to see what your roots are going to look like. Quadratic formula is no fun because it's just plug and chug. It's more fun to actually think about things. So we are going to do something the opposite way, is to see if we can introduce a perfect square into this expression like there is up here. That involves a technique called completing the square. So first thing I'm going to do is tidy this up a bit by, instead of bringing the 13 over here to the left, I'm going to chase away the 4 from the left over to the right. So there I've subtracted 4 from both sides. Now what I'm going to do is work magic. The process of completing the square is this. If you have x squared plus or minus a constant times x, there's a routine you can go through, which is to take a look at that coefficient, divide it by 2. In this case, that will be -3/2. Take that number we just made and square it, and plop the result right up here in line with everything else. In other words, add it in. So go from -3 to -3/2, square the -3/2. Now we're at 9/4, and add it in there. Now, since we've added a constant to the left side of the equation, we must also add one to the right side of the equation. The reason we did that, though, is that we just happen to have created a perfect square. The mess we just made is factorable, and even better, the constant here in the binomial is actually this one. So we've introduced a perfect square into this calculation, and then over here our little cleanup, we need a denominator of 4 on this 9 to go with that denominator of 4. So this is 36 fourths plus 9 fourths is 45 fourths. So this is the new and improved version of that expression, and now we can go solve it just like we did above by applying the square root to both sides. We will again just assert that our square root function is genuinely a function. It's only going to return the positive root. But there we have taken the square root of both sides. Let me get it in your view. That's better. And now some tidying. This particular expression, the square root of 45 is the square root of 9 times 5. The square root of 4 on the bottom is 2, and I'm adding 3 halves from the left side to the right. The reason that I broke 45 down into 9 times 5 is that now I've got a hook where I can let my square root do its thing on the 9. So the square root of 45 becomes the square root of 9 times 5, which is the square root of 9 times the square root of 5, which is 3 times the square root of 5. And then I combine the two terms with this common denominator, and I get this. And ooh, looky here, I can still factor out a 3. And that is pretty much the tidiest way that we will produce the solution to that equation. Now, if you wanted to, you could go back here and at this step where we had the square root action going on, we could apply a little plus minus and a plus minus, and we would come over here and find another similar looking solution with the effect of that extra minus sign in there. Try it out if you want.